Yesterday I had discussed about the solutions. Now continuing these chapters, today I will discuss the solubility of the gas in the liquid, that is in the solutions, and the related law, that is the Henry law. Solubility of gas in liquid, that is related with the Henry law. Henry law. This one. Now, what is the concept about the solubility? The given amount of a salt, if dissolved in a given amount of solvent, then at a particular temperature, then it is called the solubility. Now, generally, we think that the solubility will increases as the temperature will increases, and when decreases, and it will decreases. But all the things of the solubility will depend upon the nature of the reaction. If reaction is in exothermic, then on increasing temperature the solubility will decreases, and if the reaction is endothermic, then on increasing temperature the solubility will increases. So these are the concepts regarding the solubility. Now we have to discuss here the Henry law, that is the solubility of gas in the liquid. This one. So in class 11th we have studied the solubility of a gas in a given liquid is directly proportional to the pressure at a given temperature. So M is directly proportional to P. This is the, in class 11th we have already studied in chapter, that is chemical equilibrium. The solubility of a gas is directly proportional to pressure. Now, Henry, solubility of a gas is defined in the terms of the mole fraction. Mole fraction that was considered by Dalton, who was the contemporary of the Henry. So he defined solubility in the terms of mole fraction, and he said the mole fraction of a gas is directly proportional to the pressure, that is partial pressure in the liquid. So this is equal to X is equal to, this is K and P. So this X 1 by K dash, suppose it is equal to P. So this P is equal to KH into X, this one. So the Henry law now stated as, this Henry law is now stated as the partial pressure of a given mass of a gas is directly proportional to the mole fractions of the gas in the liquid at a given temperature. This is the statement of the Henry law, a statement of Henry law, a statement of Henry law, Henry, Henry law. So what we have, in terms of the Dalton, the solubility is considered in the terms of the mole fraction, and the mole fraction is directly, that is the solubility of gas is directly proportional to pressure. Here K dash is the proportionality constant, and so X is equal to K dash and P. Now this X is equal to 1 by K, this is P, and this is taken as another constant, and this constant is called the Henry constant. So the Henry law is now stated as the partial pressure of a given mass of a gas in a liquid is directly proportional to the mole fractions of the gas in the liquid at a given temperature. So what is here? KH. So this KH is called the Henry constant. This KH is called the Henry constant. And the value of KH The value of KH depends upon the temperature. The question asked what is Henry constant? The proportionality constant of Henry law is known as the Henry constant. What is this? This KH. KH is the Henry constant, and it is defined as it is the proportionality constant of a Henry law is known as what? The Henry constant. Now, the one thing, so this is about the Henry law. So we take a Henry law, P is directly proportional K into X, this one. This is the statement where KH, this is Henry constant. Now this Henry constant depends upon temperature. At different temperature, the value of different constant, the value of Henry constant is different. For a similar gases, suppose we consider nitrogen, suppose at two different temperature, that is 298 Kelvin, and another that is nitrogen gas, if we consider at 300, this is 8 Kelvin, 308 Kelvin, its value will be different. So I have noted the value. This value can be written as, this value is something it is given in the data, that is value something, that is the value is this one, 76.48 kilobar, and this value is 88.48 kilobar, this one. What does it mean? If we consider the same gases, if we write the temperature, that is at different temperature is considered as 303 Kelvin, and this is the value of Henry constant 74, and this is equal to 88.48. What this figure says, that is on increasing temperature, the Henry constant increases. Now, if Henry KH is directly proportional to, we say that is T. Now, if Henry constant increases, then what will happen? The solubility of the gas decreases. Solubility of gas decreases. Solubility of gas decreases. And a gas at two different temperature will have the different value of the Henry constant. So you tell me, suppose we have the two gases A and B, and the value of Henry constant for A is given, KHA, and the KH for B is given, and this value is lower and this value is greater or higher. So the question is asked, out of the two gases A and B, which one will be more soluble, whether A will be more soluble or B will be more soluble. So what will be our concept? As the temperature increases, Henry constant increases. Henry constant increases, solubility of gas increases. So out of these A and B gases, which one will be more soluble? Gas A will be more soluble. This is the concept regarding the Henry constant. Now, what is another point? What is the applications of the Henry law? This is application. One statement is clear, and this is application. So, what is the applications of the Henry law? We take the solubility of the CO2 gas in liquid or in soda water by increasing the pressure. That is, the CO2 is dissolved in a liquid by increasing the temperature. This is the application of the that is the Henry law. Second application, that is the scuba diver. In order to carry the oxygen cylinder or air cylinder, and this cylinder is diluted with some amount of helium. Why it is diluted with some amount of helium? In order to reduce the painful effect of the scuba diver when the diver come at the surface of the sea, or at the level, or at the surface of the sea level, and where the pressure decreases. So these dissolved gases, that is nitrogen, tends to come out, so it will put pressure on the blood vessel and it causes the bending of the bones. So these are the application of the Henry law. Now what are the some limitations? This is not limitations. So this law is only applicable for ideal solutions having applicable at low pressure and at higher temperature. At high temperature, these are the condition where this can be applied. And another condition, the solute do not undergo any association or dissociation. Remember it, what is the applications and what is the limitation. So this is all about the Henry law. That's enough. So first we know the statement, then the another thing is Henry constant. So have the capacity to define the Henry constant, and how Henry constant depends upon the temperature. So temperature is the factor that relates with the Henry constant, and if Henry constant increases, we say that is about the solubility of the gas. What is the applications? I have already discussed it, and what are the limitations. Before proceeding to the another topic, let it be clear by putting one example related with the numericals. And before that, now what is the relation P, that is KH into X. So here partial pressure is directly related to the mole fraction. So it is called the linear function of the pressure and the mole fraction. So if we plot here graph between the mole fraction and the partial pressure of the gases, what will happen? This is a straight line equation, y is equal to mx plus c. We have the concept. This is the equation like that of the straight line equation. Y is equal to mx plus c, where m is the slope and x is the axis, y is the axis. So if it is x-axis, this is y-axis, and these are the two functions, pressure and the mole fractions, right? So here the c is the intercept. So this is here is 0. So the graph will be, line will be passes through the origin, and this will be the origin of this one. So as soon as the pressure increases, the solubility of gas in terms of mole fraction will increases. That can be proved by graph, by plotting a graph. Now we take the another example for numericals in order to clear the how. So we take the numericals. I have taken this problem, that is 2 example 2.4, and page number 40 of NCRT book, right? This problem asked so many times in the final CBSE board examination. If N2 is bubbled through water at 298 Kelvin, need not to write the questions, that's why I read out the questions. If N2 gas is bubbled through water at 298 Kelvin, how many millimoles? How many millimoles? How many millimoles of nitrogen would dissolve in millimoles of nitrogen would dissolve in 1 liter of water. 1 liter of water. Assuming N2 exerts a partial pressure of, that is 0.987 bar, and the value of the Henry constant for nitrogen is given, and this value is equal to 76.48 kilobar. This one. So we apply the concept of the Henry law, theoretical concept, in that numerical to solve the problems. What is here? We see how many millimoles of nitrogen, means we have to calculate N2. Volume of water, first we write the data. Volume of water 1 liter. If we taken in milliliter, then 1000 milliliter. Now if we taken into the density of water, how much? 1 gram per milliliter. So that we know density is equal to mass by volume. So we calculate the mass of water, mass of H2O, and that comes to be 1000 gram. Right? Now we write the formula. These are the data. Right? Pn2 is given. So we write here also Pn2 0.987 bar also given, and the Henry constant is also given. Kh for N2 is 76.48 kilobar. Now when we solve this problem, one thing should be kept in your mind. The unit should be same. This is in bar, this is in kilobar. So it will be converted into bar also. 76.480. This is bar. This will be the value in the bar. Now we write the formula. Now what is the formula we write it? This is P N2 is directly proportional to KH into XN2. This is partial pressure of a gas is directly proportional to the mole fraction as per the Henry law, and here Henry constant. So we calculate, first we calculate XN2. How we calculate XN2? So we have the formula KN2 and then PN2, partial pressure of this one, and KH. From that we calculate the XN2. That can be calculated. You do it yourself. Now, and how we calculate another thing to calculate NN2. How we calculate? We know from the mole fractions definition, that is NN2 by NN2 and plus NH2O. This is the percent. Due to mole fraction, it is the ratio of the one component to that of total number of moles. Here the gas dissolved in nitrogen and it is dissolved in a water having its volume 1 liter. So we calculate the number of moles of the water and put the value here, and N2 can be calculated by using this formula. If we put this in that formula, we are able to calculate the number of moles, and it is converted into the millimoles. So how we calculate the number of moles of water? We say this number of moles of water, NH2O, so this is NH2O is equal to, that is weight of water 1000 gram, and this one is equal to 18. So this is 55.55 moles. Now we put the formula XN2, that can be calculated by using this formula, putting the value. Now NN2 is this one and this here. This NH2O comes to be 55.55. So the term NN2 in the denominator can be neglected, assuming this value comes to be very less. So we simply put NH2O. If number of moles are known, it is present in 1 liter, so it is converted into the millimoles, and the problem can be solved. There are so many problems. You apply the same concept and solve the more and more problem. So regarding the Henry law, you should know the statement of Henry law, and what is the Henry constant, you should know, and what is the temperature effect on Henry constant, what are the applications of Henry constant, and another aspects, how to solve the problem on the basis of the Henry law. This is the length. Now we consider. So you do the more and more example numerical problem to solve. There are so many problems in text problem and in exercise to try to do it. So we take another aspect. This is vapor pressure. and Raoult's law. This is vapor pressure. Vapor pressure. Vapor pressure. This one, what is vapor pressure? Simply, we take the concept for that. All the formula is, this is vapor pressure. We take the beaker, we take some liquid and it is heated, boiled, it is open. The vapor will go into the atmosphere, so there is no situation of equilibrium, and in that situation there is no, that is, there is no factor to consider the vapor pressure. Now, that can only be happens if the pot is closed one. If the pot is closed one. So what will happen? When we heat it, then the sum of the liquid will evaporate and the rate of condensation and evaporation is not equal. In the beginning, the rate of evaporation is more and here the rate of condensation is less. So what will happen? A situation arises, that is in the another diagram, we can represent it. This one and this one. These two arrows are equal. So this liquid will evaporate out and converted into the vapor. This vapor. Now this vapor will put pressure on the liquid surface, and this situation is called the equilibrium situation. So how we can define this law? That is this term vapor pressure. Sorry, how we can define the vapor pressure? That is the pressure exerted by vapor on the liquid surface in equilibrium over the on the liquid surface. The pressure exerted by vapor on the liquid surface in equilibrium at a particular temperature is known as the vapor pressure. Now this vapor pressure, so the definition is very clear. Now this vapor pressure, there Raoult's put a quantitative relation. Raoult's, R-A-O-U-L-T, Raoult's law. Raoult's put a quantitative relation between the vapor pressure and the mole fractions for the binary solutions. What is the meaning of the binary solutions? So I used to put some ink in the pen, so it should be visible to you. Now what is about the Raoult's law? So we say, we take the binary liquid. Binary liquid means the liquid having the two components, and the condition both the liquids are the volatile in nature. So this is called the binary liquid or volatile. Volatile means that can be evaporated out very easily. So the Raoult's put a quantitative relation between the vapor pressure and the mole fractions of the binary solutions which are volatile. Suppose suppose we consider the component volatile liquids as a component A and B. Let its pressure PA, this is pressure PB, the mole fraction is XA and the mole fraction is XB. According to the Raoult's law, the vapor pressure of the liquid is directly proportional of each liquid is directly proportional to the mole fractions of the liquid. So PA is directly proportional to XA and this PB is also directly proportional to XB. This is so this can be proportionality constant can be removed by using a constant PA naught and XA, and another term is PB naught. PB is equal to PB naught into XB. What is a PA naught and the PB naught? These two terms are very important. PA naught, vapor pressure of pure liquid. pure liquid, that is A. If it is A, then liquid A. And PV naught, this is the vapor pressure of pure liquid, this liquid is B. This liquid is B. So when we solve the problem, then it is very important to know the term. What is PA naught and what is PV naught and what is PA. PA is called the vapor pressures of the solutions, and this is of the liquid A and liquid B. So this is called the Henry. Mathematically, the Henry law can be explained. This is PA naught, and this is one PA. Now, if we combine the total pressure exerted, this P is equal to total pressure exerted by the binary solutions having volatile liquid. PA is equal to PA plus PB. So this PA naught XA and plus PB naught, and this is XB. So we know that XA plus XB, that is equal to what? XA and XB is equal to 1. So if we put XA, then it is 1 minus XB. So put the value in equation 1 if it is P total. This P total means that is total pressure of the solution. So we put PA naught. Put the value of XA here, 1 minus XB. And this is equal to PB naught. And this one is XB. This one is PB naught into XB. So when we solve it, P total comes to be, that comes to be PA naught minus PA naught into XB plus PB naught into XB. So this PA naught is equal to this, what? This is equal to PB naught plus PB naught minus PA naught into XB. Means the total pressure of the binary solution is equal to the total pressure of the binary solution and lies to that of the mole fractions of the one component, that is XB or either XA, we can write it. So now how graphically it can be related. So graph plot, suppose this is PA. What is PA? Is equal to PA naught into XA. So when we plot here graph, it is a straight line equation. We plot here graph, right? This is a y-axis, this is x-axis, go like that. And suppose we take PV, then PV naught, and this is XB. If you plot here graph, this one like this. This is vapor pressure axis, this is mole fraction axis, this is vapor pressure, and this is the mole fractions, right? Now, so what when, let us we see, when XA is equal to 1, then PA is equal to PA naught. When XB is equal to XA is equal to 0, then PA is equal to 0. Similarly, when XB is equal to 1, PB is equal to PB naught. When XB is equal to 0, PB is equal to 0. So the graphically it can be represented as, so this is vapor pressure axis, this is also vapor, these two graphs are combined together. This one, this is the mole fraction axis, this one is the vapor pressure axis, this one is also the vapor pressure axis. Now, here is considered XA, XA is equal to 1, then in this way PA is equal to what? PA naught. This is the vapor pressure only due to the component. This one is A. Now, and when we consider XB is equal to 1, then it is equal to PB naught, and it comes to be PB naught. Now, from this it will give you a straight line. So when XA will decreases, XA here comes to be 1, means its vapor pressure going to decrease, and this is equal to XA is equal to 0, then PA is equal to 0, that is here, this is equal to the vapor pressure is comes to be what? That is 0. Now when XB increases, vapor pressure increases, so the curve like this is obtained, right? So this is curve is written as PA, and this one is PA naught, XA, and this one is also PB, and this one is also PB naught, XB. Now the total vapor pressure will also give lie between the two component. So this P total is equal to PA plus PB. So we can write here P total is equal to PA plus PB, and it can be written as a expanded form PA XA plus PB naught into XB, and this is equal to P total. This is called that is related with the Raoult's law for your binary solutions of two volatile liquids. This one. So there is one problem. Raoult's law, there is one problem. Similarly, now the question arises: how we calculate the mole fractions in the vapor phase? So remember it. Now the another is calculation of mole fraction. Calculate formula for calculation of mole fraction in vapor phase. Fraction in vapor phase. That is, we consider the component that is YA, that is the mole fraction of A in vapor phase, mole fraction of A in vapor phase, and YB, mole fraction of B in vapor phase. So we have the formula. This is YA is equal to. So YA is equal to mole fraction of a component in vapor phase, that is partial vapor pressure, divided by P total in vapor phase. Mole fraction of a component in vapor phase. This is the formula. Similarly, we can write the mole fractions for the component B. So this can be written as YB is equal to, this YB is equal to, this is PB by P total. So this is the, so after discussing the Raoult's law for a volatile component, I come on the conclusion. First we know the mathematical expression for the Raoult's law. This one is PA is equal to PA naught XA, then PB, this is equal to PB naught XB, and another P total, that is PA naught XA plus PB naught XB. Then total pressure can be calculated. The mole fraction of a component in vapor phase YA is equal to, This is partial vapor pressure of a component by P total and mole fraction of a component in vapor phase, that is B, that is equal to PV into P total. By using that formula, this formula is very important. So we should have the concept about the Raoult's law for the volatile component, and we should have the command over the formula, and this formula helps to solve the numericals. So these are in the box. These are very important. These are very important. So these are very important. These are very important. By using that formula, we are able to solve the problem. Now we come to the problems. So I will only give you the example, and because the time is going on, so we write example number 25 and page number 48. Page number 48 of NCERT book. So these problems helps to solve the this problem helps to solve the problem on the basis of the Raoult's law. If you have the theoretical concept, if you understand this concept very clearly, then you can only solve this problem. Once I read out the problem, it is given, so it is your task, you will do at your home, and when we meet tomorrow, then I will discuss, so whether it will be solved by you or it is not solved by you. So the reason is the vapor pressure of, the problem is the vapor pressure of chloroform. The vapor pressure of chloroform, right, and the dichloromethane is given, and it is given as 200 mmHg, and this is 450 mmHg. This is the unit. Always write it with a unit. Calculate the vapor pressure of the solution obtained by mixing. The amount of the chloroform is given, amount of the dichloromethane is given, right? And the another problem, calculate the total vapor pressure of the solution. The vapor pressure of the chloroform and the dichloromethane is given, and what is the value? It is given, and the amount is given, its amount weight is given, its weight is given. The problem, you calculate the P total. How you will calculate? Apply the concept, right? And the second problem, you calculate the mole fractions of the chloroform in the vapor phase and the mole fraction of the dichloromethane in the vapor phase, and this is the problem that totally depends upon this theory. So today is the last topic. So finally I want to conclude this today's concept, that is Henry law, a statement, Henry constant, a statement, that is definition. Henry constant depends upon temperature, how it affects the solubility of the gases, and the another one is numerical problem and its application and the limitation. Then we come on the vapor pressure, and I defined the term what is vapor pressure and how it is related with the Raoult's law. So I explained the Raoult's law very clearly for the binary solutions which are of the two volatile liquids. Mathematically it can be proved, and how the graph is varies, and how the total vapor pressure we are able to calculate. And we also, I have given you the formula to calculate the mole fractions of the component in the vapor phase by using this formula, and I projected you the one problem based on this theoretical concept. You try to solve it. When tomorrow I will meet you, then you will tell me, okay, it is solved by yes, or either I have to solve it. Okay, this is so. आपको ये वीडियो मेरा कैसा लगा, इसको आप मैक्सिमम शेयर करें, सब्सक्राइब करें और डाउनलोड करें. यदि अच्छा हुआ तो हमें इंकरेजमेंट मिलेगा और हम आगे फिर इसी तरह से आपका क्लास कंटिन्यू करेंगे. ओके, थैंक यू.